10 billion light years away. Something exists that should not a star, not a galaxy, something worse, a mouth in space, a region so dense, so impossibly massive that even light, the fastest thing the universe permits, cannot escape once it crosses the threshold. Scientists call it a black hole. But what we're about to explore transcends that simple name. 66 billion times the mass of our Sun, compressed into a single point. An event horizon so vast that light itself would take 2 weeks just to cross from one edge to the other. And here's what keeps astrophysicists awake at night. This thing should not exist. Not yet. Not now. Not this large. This soon after the Big Bang. The early universe was supposed to build slowly, patiently. By every equation we've written, every model we've tested, TON 618, that's what we call it, should have needed far longer to grow this massive. Yet there it is, ancient, feeding, sending something toward us that has been travelling for over 10 billion years. Something that's arriving right now, tonight. And what it's telling us is reshaping everything we thought we knew about how the cosmos actually works. But here's the deepest mystery. We still don't fully understand why it exists at all. If you're ready to confront a cosmic enigma that challenges the very foundations of modern physics, subscribe now. This is a journey into the impossible. There is a place in the universe where the rules quietly stop working. Not dramatically, not with any sound or flash of light, just a slow, gradual fading of everything familiar. A place where matter falls inward and never returns. Where light itself loses its ability to climb back out. Where the geometry of space bends so completely around a single point that the concept of a way ceases to exist. You are drifting toward that place now, not close enough to feel it, not close enough for anything to change around you, but close enough in your imagination to begin sensing its presence. The way you might sense a very large, very quiet thing standing just behind you in a dark room. Not threatening, just there. Enormous and patient and older than almost anything else in the observable universe. This place has a name. A strange, almost accidental name that carries none of the weight you might expect something like this to have. TON 618. It was first noticed in 1957. Not discovered, really. Noticed. The way you might notice a smudge on a window without thinking much about it. Astronomers at the Tonantzintla Observatory in Mexico were conducting a broad survey of the sky, cataloguing faint objects on photographic plates. Thousands of entries. Hundreds of unremarkable blue specks scattered across the images like dust on glass. Entry number 618 on that list looked like a star. It was faint. Bluish. Perfectly ordinary by the standards of a sky full of ordinary things. Nobody lingered on it, nobody felt anything shift when they recorded it and moved on. It was simply filed away, number 618, and the survey continued. For 15 years, that is all it was. A catalogue entry, a faint blue dot on old photographic paper, sitting quietly in an archive while the world moved on around it. And then, slowly, something changed. By the early 1970s, the instruments astronomers used to study light had grown considerably more sensitive. Spectrographs, devices that split light into its component colours and reveal the chemistry and motion of the object producing it, had become precise enough to look more carefully at objects that had once seemed unremarkable. When those improved instruments turned toward entry number 618, what they found was not a star. The light was wrong, its colours were stretched, shifted dramatically toward the red end of the spectrum. In a way that only happens when an object is moving away from us at extraordinary speed, or when its light has been travelling for so long through an expanding universe that space itself has pulled the wavelengths apart like taffy. When astronomers calculated what that redshift meant, the answer was quiet and enormous. The light from Ton 619 had been travelling for just over 10 billion years. 10 billion years. The universe itself is only about 13.8 billion years old. The light captured on those photographic plates had left its source when the cosmos was barely a quarter of its current age. Before our sun existed. Before our solar system had assembled itself from the remnants of older dying stars. Before Earth had formed, cooled, gathered its oceans, or done any of the billions of years of patient geological and biological work that eventually produced a species curious enough to point telescopes at the sky and ask questions. That light had been travelling all of that time, and the object producing it was not a star, it was a quasar. That word, quasar, is a compressed version of the phrase quasi-stellar object. It describes something that looks like a star but isn't. Something that looks like a single bright point of light, but is actually the blazing active core of an entire galaxy. At the centre of that galaxy sits a supermassive black hole, and around that black hole swirls a vast disk of infalling matter, gas, dust, the remnants of stars heated by friction and gravitational energy to temperatures so extreme that the disk outshines every star in the galaxy surrounding it, sometimes by a factor of thousands. That impossible brightness is what we see from Earth. That is what registered on those photographic plates in 1957 as a faint blue star. Not a sun. Not anything close to a sun. The collective death glow of an ocean of matter spiralling into something that cannot be seen directly, only inferred from what it does to everything around it. This is what a black hole actually is, at its most fundamental. Not a vacuum cleaner, not a mouth reaching across space to swallow distant things. A black hole is simply a region where mass has been compressed into a space so small and the resulting gravity becomes so concentrated that even light, the fastest thing in the universe, cannot generate enough speed to escape once it crosses a certain threshold. That threshold has a name, the event horizon. Think of it less as a surface and more as a point of no return, a one-way door written into the fabric of space itself. Cross it moving inward, and the universe behind you, the stars, the galaxies, every photon of light from every direction, stops being a future you can return to. It becomes something you can only receive passively as you continue falling toward a centre that grows more incomprehensible the closer you approach. Most black holes in the universe fall into two broad families. The first family forms when massive stars reach the end of their lives and collapse. These stellar mass black holes weigh anywhere from a few times to a few dozen times the mass of our Sun. They are compact, dense, and in cosmic terms, relatively modest. The second family sits at the centres of galaxies. These are the supermassive black holes, and they are on an entirely different scale. Our own Milky Way has one. It is called Sagittarius A, and it weighs approximately 4 million times the mass of our Sun. That number sounds extreme, and by any human standard it is. But then there is Ton 618. And Ton 618 does not belong to either family in any comfortable sense. At somewhere between 40 and 66 billion times the mass of our Sun, depending on which measurements and revisions you consult, TON 618 sits so far beyond the range of what astronomers expected to find that they had to reach for entirely new language to describe it. They call objects in this range ultramassive, a word invented specifically because no existing word was adequate. Sagittarius A, the black hole at the heart of our own galaxy, weighs 4 million solar masses. Ton 6118 weighs up to 66 billion. The difference between those two numbers is not a difference of degree, it is a difference of kind. Sagittarius A is enormous. TON 618 is something the universe should have needed far more time to build, and yet there it sits, ancient and incomprehensible, its light already crossing the final few miles of a 10 billion year journey to land in the mirrors of our telescopes tonight. And this is where the story begins to deepen. Because TON 618 is not simply large. It is large in a way that sits uncomfortably against everything we thought we understood about how the universe assembles its most extreme structures. Its size, its age, its location in the very early cosmos, all of it points towards something our models of cosmic evolution still struggle to account for cleanly. The mouth at the edge of everything is not just a record holder, it is a question. One of the largest and most patient questions the universe has ever posed to the small, curious species living on a quiet blue planet 10 billion light-years away. And the universe has been waiting a very long time for an answer. There is a certain kind of number that the human mind simply was not built to hold, not because we lack intelligence, not because the mathematics is too complicated, but because our brains evolved on a small planet, surrounded by things we could touch and measure and walk around. Things with edges, things with weight we could feel in our hands. Our sense of scale was built for forests and oceans and mountain ranges, for distances we could cross in a day, or a lifetime. And then the universe offers you a number like 66 billion solar masses, and the mind reaches for it and finds nothing to hold on to. So let us try something different. Let us build the scale slowly, one step at a time, until the shape of what Ton 618 actually is begins to settle into something you can almost feel. Rather than simply calculate, begin with the Earth. You know the Earth, you live on it. It is large enough that no single person has ever seen all of it at once with their own eyes. Large enough that its oceans hold a volume of water so enormous that every river on every continent could flow into them for thousands of years without filling them. Large enough that its atmosphere, thin as it is, produces weather systems visible from space. Now place 1.3 million Earths inside the Sun. That is how large our Sun is relative to our planet. You could fill it with Earths the way you fill a jar with marbles, and you would need 1.3 million of them before the jar was full. The Sun, by the standards of our daily experience, is incomprehensible. Now take that Sun, and imagine 66 billion of them, not lined up in a row where you could at least trace the length of the line. Compressed, pulled together by gravity into a single point so dense. That space itself curves around it like a blanket pulled toward a drain. Every star you have ever seen with your naked eye on a clear night. Every constellation. The full sweep of the Milky Way across a dark summer sky. All of that combined, and still falling short of what Ton 618 contains. And slowly, the number begins to mean something different. Not a figure on a page. Something else. Something that sits in the chest rather than the mind. The event horizon of Ton 618 has a radius of roughly 1,300 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. That distance, the full stretch between our planet and the star that warms it, is 1 unit of measurement on the scale we are now working with. Pluto, the most distant major body in our solar system, orbits at around 40 of those units, 40 times the Earth-Sun distance. Far enough that sunlight takes over 5 hours to reach it. Far enough that from Pluto's surface, our Sun looks like nothing more than a very bright star among other stars. The event horizon of TON 619 reaches more than 30 times past Pluto in every direction. From edge to edge, passing through the centre, it spans roughly 2,600 astronomical units. You could place dozens of complete solar systems, Sun to Pluto, end to end across that span, and still find room remaining. Not a few solar systems, dozens. But even that image, as large as it feels, is still just a flat comparison. A ruler laid against something that has no interest in being measured. Now consider light. Light travels at approximately 186,000 miles per second. In a single second, it crosses a distance greater than 7 times the circumference of the Earth. In 8 minutes, it travels from the Sun to our planet. In about 4 hours, it reaches the orbit of Neptune. In a little over 5 hours, it reaches Pluto. A beam of light crossing the event horizon of TON 618 from one side to the other would take approximately 2 weeks. 2 weeks for light, the fastest thing the universe permits, to cross a single structure in space. Not a galaxy. Not a cluster of galaxies. One object. One whole. Sit with that for a moment. Let the silence around that fact settle in the way silence settles in a very large, very empty room. And this is where the geometry begins to do something stranger still. Imagine, purely in the realm of thought, because physically this would be impossible long before you arrived, that you could drift toward the edge of that event horizon. Close enough to observe, close enough to feel the subtle wrongness of the space around you. The first thing you would notice is the light. Not darkness. Light, but light behaving in a way that nothing in your experience has prepared you for. The stars behind you, the ones you passed on your way here, would begin to appear in front of you. Space would be curving so severely around the mass below that photons travelling in nearly every direction would be bent, looped, redirected. The entire sky would rearrange itself. Galaxies you knew were behind you would appear above, smeared into thin luminous rings, halos of stretched light circling the one point in the universe where everything converges, and below you, nothing. Not darkness in the way a starless patch of sky is dark. Something more complete than that. A perfect, absolute circle of absence. No texture, no depth, no surface to focus on. Your eyes would search for something to register and find only the bottom of everything. A place where the concept of further in stops having meaning. Meanwhile, your watch would be ticking. But slowly, something changes in what that ticking means. Time near an object this massive does not flow at the same rate as time far from it. This is not a metaphor or a poetic interpretation. It is one of the most precisely tested predictions in all of physics. Gravity curves not just space, but time itself. The stronger the gravitational field, the slower time moves within it relative to time measured somewhere far away. Near the edge of TON 619's event horizon, this effect would be extraordinary. A single minute of your time, one quiet minute of breathing and observation, would correspond to something on the order of a century passing on Earth. Not a long human life. A century. 100 years of history, change and loss on the small blue world you left behind, compressed into the span of 60 seconds of your experience. Drift a little closer, and the ratio shifts further still. The universe beyond the horizon would be aging around you at a rate your mind cannot map onto anything familiar. Stars would be born and die. Civilizations would rise and fall. And you would simply be floating, watching the light bend, your watch ticking its calm and increasingly irrelevant seconds. This is the geometry of TON 618. Not what it does, not what it eats or how it grows, or what it means for the universe that it exists. Simply what it is, in terms of shape and scale and the behaviour of space and time in its presence. And even this, only the geometry, is enough to quietly dismantle the comfortable sense of scale most of us carry through our lives without ever examining it too closely. We think of ourselves as small but significant. We think of our solar system as vast but comprehensible. We think of the universe as large but bounded by numbers we have at least written down. And then Ton 618 simply exists. Patient, ancient, geometrically extraordinary, sitting at the centre of a distant galaxy whose name we do not even know, curving space around itself in a region so large that light takes 2 weeks to cross it, while 10 billion years of its own history travel toward us 1 photon at a time. It does not need to do anything dramatic to be what it is. The scale alone is enough. There is something almost peaceful about a quiet black hole, one that simply sits at the centre of its galaxy, pulling nearby stars into slow wide orbits, bending light gently around itself, accumulating mass in patient increments over billions of years. Our own Milky Way's central black hole, Sagittarius A, is largely like this right now. Quiet. Settled. Not actively consuming anything significant, just present. Like a deep well at the centre of a spinning city, mostly still, mostly dark. Ton 618 is nothing like that. Ton 618 is awake. And when something this large is awake and feeding, the universe around it stops being quiet in any sense of the word. The term for what Ton 618 is, what it is actively doing, is a quasar, and to understand why a quasar is so different from a quiet black hole, you need to understand what happens when matter begins falling towards something with this much gravitational pull. Matter does not fall straight in, it spirals. The way water spirals toward a drain, gas and dust approaching a black hole begin to rotate around it, gradually tightening their orbit, slowly losing energy, slowly descending. As more material joins from the outside, and the inner layers press closer to the event horizon, everything compresses. And compression generates heat, not the gentle warmth of a campfire, not even the ferocious heat at the core of our sun. The accretion disk, the name for this vast, flat, spiralling ocean of infalling matter, reaches temperatures of millions of degrees in its innermost regions. At those temperatures, matter does not simply glow. It radiates across every frequency of light simultaneously. Visible light. Ultraviolet. X-rays. The disk becomes one of the most energetically violent structures the universe is capable of producing, and around a black hole the size of Ton 618, that disk extends for distances that make the word large feel inadequate all over again. The accretion disk surrounding Ton 618 would stretch outward for light weeks in every direction from the event horizon, not light seconds, the way we measure distances within our solar system. Light weeks, the disk alone, just the flat ring of doomed glowing matter, would dwarf most things we consider enormous in our cosmic neighbourhood. Stars that drift too close to this system do not fall in cleanly. They never reach the event horizon as whole objects. Long before they could, the difference in gravitational pull between the side of the star facing Ton 618 and the side facing away becomes so extreme that the star is simply pulled apart. Stretched. Unravelled into long, thin streamers of superheated gas that spiral into the disk and join the slow procession inward. These events have a name. Astronomers call them tidal disruption events. We have observed them happening around smaller black holes. Brief, brilliant flares of light as a star is torn apart and consumed. Around those smaller objects, a single stellar disruption is a notable event, something worth studying carefully. At the scale of TON 618, an entire cluster of stars could be slowly consumed over the span of a human lifetime, and the quasar would register it, the way an ocean registers a cup of water poured into it. But slowly, something even more extraordinary comes into focus when you look at the numbers. The luminosity of TON 618, the total amount of energy it radiates every second, is estimated at approximately 140 trillion times the brightness of our Sun. 140 trillion. Numbers this large tend to slide past the mind without leaving much impression, so let us translate it into something with more texture. Take the Milky Way. Our home galaxy, every star burning within it, all 400 billion of them, from the smallest red dwarfs barely large enough to sustain nuclear fusion, to the enormous blue supergiants burning through their fuel in a few million years. Every single one of them radiating their light simultaneously into the darkness. Now place that entire galaxy beside TON 618. The quasar would outshine it by a factor of several thousand, not slightly brighter, not twice as bright, several thousand times more luminous than an entire galaxy of 400 billion stars. One object, one feeding black hole at the centre of one distant galaxy, outshining everything around it so completely that the hundreds of billions of stars in its own host galaxy are essentially invisible in comparison, washed out by the light of the disk surrounding their central black hole. This is what registered on those photographic plates in 1957. As a faint blue speck, that faint blue speck, so unremarkable that nobody looked twice at it for 15 years, was the most luminous single object that has ever been confirmed in the observable universe. Dimmed to near invisibility by 10 billion years of travel and the expansion of space, and still bright enough to leave a mark on photographic paper. And here is where something quietly important needs to be understood. That light, the impossibly bright glow of the accretion disk, is not TON 618 itself. It is a symptom, a visible side effect of a process happening at the edge of the event horizon. The black hole itself remains perfectly dark, perfectly invisible. What we see is only the material that has not yet crossed over. The last glow of matter in the final stages of its long inward spiral. Everything we know about TON 618 comes from studying that glow. The mass estimates, the size calculations, the distance measurement, the age, all of it derived from analysing light. That was produced by matter that no longer exists in any form we would recognise, matter that fell across the event horizon billions of years ago, long before the Earth formed, long before our Sun ignited. We are reading the last diary entries of something that vanished before our world began. There is one more aspect of an active quasar worth pausing on, because it adds another layer to what TON 618 is doing in its distant corner of the early universe. Many active black holes produce jets. As matter spirals inward through the accretion disk, magnetic fields generated by the rotating plasma can focus and accelerate some of that material outward, along the black hole's rotational axis, not inward, outward, at speeds approaching the speed of light. These relativistic jets can extend for hundreds of thousands of light years, far beyond the boundaries of the host galaxy itself, blasting energy and particles into the surrounding cosmic environment. These jets reshape everything they touch. They heat the gas between galaxies. They suppress star formation across enormous regions of space. They are, in a very real sense, one of the primary ways that the most massive black holes regulate the growth and structure of the universe around them. TON 619, actively feeding at the rate implied by its luminosity, would have been producing jets of extraordinary power. During the period its light was being emitted, energy outputs that influenced not just its immediate surroundings, but potentially vast regions of the early cosmic web, the network of gas filaments and voids. That forms the large-scale structure of the universe. One object shaping the architecture of the cosmos around it, sending its influence outward in every direction, including in the form of ancient light, toward a small planet that would not exist for another 6 billion years. This is what it means for TON 619 to be awake. Not simply large, not simply massive, actively transforming its environment, consuming stars, radiating energy equivalent to trillions of suns, sending jets of accelerated matter beyond the edges of its own galaxy, and doing all of this while sitting at a distance so vast that its light takes longer to reach us than the Earth has existed. The glow is just the beginning. Underneath the glow, something much older and much stranger is waiting. And that is what we turn to next. There is a certain comfort in believing the universe follows rules, not rigid, unforgiving rules, but consistent ones, patterns that hold across time and distance, principles that apply whether you are studying a stone falling from a cliff on Earth or a galaxy spinning at the edge of the observable universe. Physics, at its most fundamental, is the art of finding those patterns and trusting them. And for a long time, when it came to black holes, the patterns seemed reliable. We understood how they formed. We understood how they grew. We had equations that described the process with remarkable precision. And within the comfortable range of objects we had studied, stellar mass black holes, galactic center black holes, even the larger supermassive ones, those equations worked beautifully. Then TON 61 Hop arrived, and quietly, without drama, it broke almost everything. To understand why TON 618 is so deeply problematic for our models, you first need to understand how black holes are supposed to grow. A black hole gains mass in two primary ways. The first is accretion, the process we explored in the previous section. Matter falls inward, joins the accretion disk, spirals toward the event horizon, and eventually crosses over. Each infalling star, each cloud of gas, each dust particle adds incrementally to the total mass. It is a slow, steady process, patient in the way only cosmic timescales can be. The second way is mergers. Two black holes, drawn together by mutual gravity, spiral toward each other over millions or billions of years, and eventually collide. When they merge, their masses combine. A black hole of 10 solar masses merging with one of 15 produces something close to 25 solar masses, minus a small amount radiated away as gravitational waves during the collision. Mergers can produce rapid jumps in mass, but they still require time. Time for the objects to find each other, time for their orbits to decay, time for the collision itself to complete. Both processes, accretion and mergers, are fundamentally limited by something physicists call the Eddington limit. The Eddington limit describes the maximum rate at which a black hole can realistically feed. As matter falls inward and heats up in the accretion disk, it radiates enormous amounts of energy outward. That outward radiation exerts pressure on the infalling material, pushing it away from the black hole even as gravity is pulling it in. At a certain accretion rate, the outward radiation pressure balances the inward gravitational pull. Feed faster than this limit and the radiation itself blows the infalling material away before it can be consumed. This creates a natural speed limit for black hole growth. Even a black hole feeding at the absolute maximum rate the Eddington limit permits, essentially as fast as physics allows, still only doubles its mass every few tens of millions of years. That sounds fast in human terms. In cosmic terms, it is a measured, unhurried process. Now apply that speed limit to TON 618. Start with the most generous possible seed, a black hole of perhaps a few hundred solar masses formed from the collapse of one of the earliest massive stars. Run the Eddington limited accretion rate forward in time. Watch the mass double, and double again, and double again, in patient increments across millions of years. The universe at the time TON 618's light was emitted was less than 4 billion years old. The math does not close. You cannot grow 66 billion solar masses from a few hundred in less than 4 billion years, even at the theoretical maximum feeding rate. The numbers simply do not reach. It is not a small discrepancy that better measurements might resolve. It is a fundamental gap between what our models predict and what TON 618 actually is. And this is where the universe stops being comfortable. But slowly, something deeper becomes clear. TON 618 is not an isolated problem. It is the most extreme example of a broader pattern that has been emerging as our telescopes reach further and further back in cosmic time. Wherever we look in the early universe, in the first few billion years after the Big Bang, we find black holes that are too large for their age. Not slightly too large, significantly too large. Objects that should have needed far more time to accumulate their mass than the universe had actually provided when their light was emitted. For years, astronomers assumed these were edge cases, statistical outliers, objects that had somehow managed to grow unusually fast through a particularly favourable combination of circumstances. TON 618 was the most dramatic example, but perhaps not representative of anything more general. Then the James Webb Space Telescope began operating, and the edge cases stopped looking like edge cases. But that is a story for a later section. For now, the important thing is this. TON 618 forced a genuine reckoning with our models of black hole growth, not a minor adjustment, a fundamental reassessment of what the early universe was capable of building and how quickly it was capable of building it. The problem at its core is one of time. The universe had a beginning, approximately 13.8 billion years ago, in an event we call the Big Bang. Space and time and energy came into existence together. For the first few 100,000 years, the universe was too hot and dense for atoms to form. Light could not travel freely. Structure could not emerge. Only after that initial period of cooling did the first atoms appear. Only after further cooling and the slow accumulation of matter under gravity did the first stars begin to ignite, perhaps 100 to 200 million years after the Big Bang. And only after those first stars lived and died did the first black holes of stellar origin form. That leaves a window of less than 4 billion years between the formation of the first stellar black holes and the moment when TON 618's light was emitted, already carrying the signature of something with tens of billions of solar masses. 4 billion years sounds long. In human terms, it is almost incomprehensible. But measured against what TON 618 would have needed to grow through conventional accretion alone, it is nowhere near enough. Something else must have happened. Something the universe did in its earliest, most energetic, most chaotic period that our current models either cannot fully capture or have not yet correctly identified. And here is what makes this genuinely important, rather than simply academically interesting. TON 618 is not just a record, It is evidence, hard, measurable, photographic evidence, that the early universe operated in ways our physics does not yet fully describe. Every time our equations fail to account for its existence, they are telling us something. Not that physics is wrong, but that our understanding of physics is incomplete. There are regions of behaviour, extreme scales, extreme densities, extreme timescales, where the rules we have written down begin to show their edges, where the map we have drawn of the universe starts to run out of detail, and the territory beyond it remains unmapped. Ton 619 sits at one of those edges, patient and ancient and entirely indifferent to the difficulty it causes for the small species 10 billion light years away, trying to explain it with equations written in the last few centuries. The universe built something that, by our rules, should have taken much longer to build. It did so early, and it did so at a scale that remains unmatched by anything else we have confirmed, and every photon of light arriving from that direction carries the same quiet, persistent message. Your rules are a beginning, not an ending. The universe is larger and faster and stranger than the equations written so far can fully hold, and somewhere in the darkness, Ton 618 has been waiting 10 billion years for us to catch up. When something in the universe refuses to fit inside the equations we have built to describe it, science does not simply stop and declare the problem unsolvable. It pauses, it reconsiders, and then slowly it begins proposing alternatives, not wild guesses, carefully reasoned possibilities drawn from the edges of what physics permits, ideas that stretch the boundaries of what we consider normal, but do not break the fundamental laws that govern mass, gravity, time, and energy. Theories that acknowledge we may have been working from incomplete assumptions about how the early universe actually behaved. In the case of Ton 619 and the other impossibly large early black holes we have found, astronomers have developed three main ideas. None of them are completely comfortable. None of them can be tested directly, not yet, because the events they describe happened billions of years ago. In regions of space we cannot visit or observe directly, but each one offers a different answer to the same quiet, persistent question. How did something this large form so quickly? Let us walk through them, one at a time. The first idea is called direct collapse. In this scenario, the early universe skipped a step we long assumed was mandatory. Normally, stars form first. Giant clouds of primordial gas, mostly hydrogen and helium left over from the Big Bang, collapse under their own gravity, ignite nuclear fusion in their cores, and become stars. Those stars live for millions or billions of years, then die. The most massive ones collapse into black holes at the end of their lives, producing stellar mass black holes of perhaps 10 or 20 or 50 times the mass of our Sun. From there, those black holes grow slowly through accretion and mergers across cosmic time. But what if, in certain rare and specific conditions, that entire first step was bypassed? What if some of the earliest gas clouds in the universe were so large, so massive, and so free of heavier elements, the metals produced inside stars, that they collapsed directly into black holes without ever forming stars at all? This is the heart of the direct collapse scenario. Under very particular conditions in the infant cosmos, a primordial gas cloud could collapse straight into a black hole of perhaps 100,000 or even 1,000,000 solar masses. Not a few dozen, hundreds of thousands. Starting with a seed that large gives you an enormous head start. A black hole born at 1,000,000 solar masses does not need to double its mass as many times to reach tens of billions. the number of doublings required shrinks dramatically. Feed that seed black hole at or near the Eddington limit for a few billion years, and the math starts to work. You can reach something like ton 618 in the time available. The challenge is understanding whether such conditions actually existed. For direct collapse to work, the gas cloud needs to stay cool enough to avoid fragmenting into smaller clumps that would form individual stars. It needs to avoid contamination by metals, elements heavier than helium, which would allow the gas to cool too efficiently and fragment. And it needs to collapse in an environment where intense ultraviolet radiation from nearby young galaxies keeps the hydrogen ionized and unable to cool normally. These are very specific requirements, not impossible, but rare, and difficult to confirm because the regions where this would have happened existed over 10 billion years ago, far beyond what most telescopes can observe in useful detail. Direct collapse remains one of the leading explanations, but it is built on conditions we have not directly observed and may never be able to fully verify. The second idea is runaway mergers. Imagine the very dense cores of the earliest galaxies, regions where stars formed rapidly, lived briefly, and died in enormous numbers, where the space between objects was much smaller than it is in the quieter, more settled galaxies we see around us today. A cosmic city packed far too tightly with massive, unstable structures. In such an environment, collisions would not be rare events. They would be frequent, almost inevitable. Massive stars would collide with other massive stars, producing even larger stellar remnants. Those remnants would collapse into black holes. Those black holes would spiral inward toward the galactic center, drawn by the collective gravity of everything around them. And there, in the densest region of the galaxy, they would begin merging with each other in rapid succession. Each merger adds mass. Each additional mass increases the gravitational pull on nearby objects, drawing in more black holes, more gas, more infalling material. The process feeds itself, not slowly across billions of years, but rapidly on timescales of millions of years. In what physicists call a runaway process, repeat this cycle fast enough in the chaotic cores of infant galaxies, and you could build something extraordinarily massive in a relatively short time. This scenario has the advantage of relying on processes we know happen. Black holes merge. We have detected the gravitational waves from such mergers directly. Using instruments like LIGO and Virgo, we know galactic centers are dense dynamic environments, where interactions between massive objects are common. The challenge is scale and speed. Even under runaway conditions, you still need a lot of mergers happening very quickly, one after another, in the same location, and each merger radiates away a portion of the combined mass as gravitational waves, energy lost to the system that slows the overall growth slightly. The numbers work better than they do with pure accretion, but they still require the early universe to be far more chaotic and collision-rich than we once believed. It is plausible. But it pushes our models of early galaxy formation into territory where observations are still sparse and uncertain. The third idea is the most speculative, and in some ways the most unsettling. It suggests that some black holes were never born from stars at all, that they formed in the very first moments after the Big Bang itself, in the chaotic, unimaginably dense conditions that existed before the first atoms, before the first light, before anything we would recognize as structure. These are called primordial black holes. In the fractions of a second after the Big Bang, the universe was not smooth. There were tiny fluctuations in density, quantum ripples frozen into the fabric of space, during the period of rapid expansion called inflation. In regions where those fluctuations were extreme enough, matter could have collapsed directly into black holes, while the universe was still unimaginably hot and dense. If primordial black holes exist, they would have been present from the very beginning, not products of stellar collapse, not results of direct gas cloud collapse, direct artifacts of the universe's birth. And if they existed, they could have started growing immediately, long before the first stars ignited. This scenario solves the time problem almost completely. A primordial black hole could have been accumulating mass for hundreds of millions of years before the first galaxies even began to form. By the time those galaxies assembled themselves around these ancient seeds, the black holes would already be enormous, millions or billions of solar masses, and positioned perfectly at the galactic centers to continue feeding and growing. The challenge is that we have no direct evidence primordial black holes exist. We have looked for them. They should produce detectable effects if they are common enough. But so far, none of those effects have been conclusively observed. The idea remains theoretical, elegant, mathematically consistent, and entirely unproven. If Ton 618 began as a primordial black hole, it was never a thing that became what it is. It was born in the first chaos of existence itself, and has been feeding ever since, a structure older than stars, older than galaxies, older than almost anything else in the observable universe, except space and time themselves. These are the three main answers currently on the table. Direct collapse, runaway mergers, primordial origins. Each one forces us to admit something uncomfortable about the early universe, that it was capable of building extreme structures through pathways we did not initially consider, that our equations describing how mass accumulates and black holes grow may be missing important mechanisms that only operate under the specific, unrepeatable conditions. Of the cosmos in its infancy, we do not know which answer is correct. We may never know with absolute certainty. The events happened too long ago, too far away, under conditions we cannot recreate or observe directly. But Ton 618 does not care whether we understand it. It simply exists. Patient and ancient. A question the universe posed 10 billion years ago, still waiting quietly for the small species on the distant blue planet to finish working through the mathematics. There is a question that sits quietly in the back of the mind whenever something this large and this strange enters the conversation. It is not always spoken aloud. Sometimes it does not need to be. But it is there, patient and persistent, waiting for the right moment to surface. The question is simple. Should we be worried? Is Ton 618, in any measurable sense, heading toward us? Is there something we need to prepare for, however distantly? Some consequence of its existence that might eventually reach across the vast emptiness between galaxies and touch this small blue world in a way that matters? The answer has two parts, and both of them are important. The first part is clean and reassuring. Ton 618 itself, the physical object, the ultramassive black hole sitting at the centre of its distant host galaxy, is not heading toward us. In fact, it is moving in the opposite direction. Not because it is fleeing, not because anything is pushing it away, but because the universe itself is expanding, and that expansion is carrying Ton 618. And the galaxy it inhabits, farther from us with every passing moment. This is one of the fundamental truths about the cosmos we live in. Space is not static. It is not a fixed stage on which objects move. Space itself stretches. The distances between galaxies that are not gravitationally bound to each other increase over time. Not because the galaxies are moving through space in the traditional sense, but because new space is continuously being created between them. The farther away a galaxy is, the faster it appears to recede from us. This is called the Hubble expansion, named after Edwin Hubble, who first measured this effect in the 1920s. TON 618 is over 10 billion light-years away. At that distance, the expansion of space is carrying it away from us at a significant fraction of the speed of light, and the expansion is accelerating, not slowing down, not holding steady, getting faster. Driven by something physicists call dark energy, a poorly understood component of the universe, that acts as a kind of anti-gravity on the largest scales, pushing space to expand at an ever-increasing rate. What this means in practical terms is straightforward. The physical distance between Earth and TON 618 is growing. Right now, as you read this. It was larger a moment ago than it was a minute before that. It will be larger tomorrow than it is today. And barring some profound shift. In the fundamental physics governing cosmic expansion, something we have no reason to expect, that distance will continue increasing forever. TON 618 will never grow closer to us. It will never pose a gravitational threat, even if it could somehow reach across space. To pull on distant objects which it cannot, the expansion of the universe ensures that the gap between us and it will only widen with time. In the most literal, measurable sense, TON 618 is retreating into the darkness, slowly, inevitably, and without any possibility of reversal. So the answer to the question, is TON 618 heading toward us? Is no. Physically, gravitationally, measurably, it is not. But then there is the second part of the answer, and this part is more complicated. Because something from TON 618 is heading toward us, has been heading toward us for more than 10 billion years, is arriving right now, at this exact moment, in observatories scattered across the surface of this planet. Light, the photons emitted by the superheated accretion disk, surrounding that ancient black hole, radiating outward in all directions, a tiny fraction of them aimed, by nothing more than chance, toward the region of space where our sun would eventually form and our planet would eventually cool. And a species capable of building telescopes would eventually emerge. Those photons have been travelling since the universe was less than 4 billion years old, and they are still arriving. Every clear night more of them complete the journey. Every observation we make of TON 618 captures ancient light that has spent longer travelling toward us than our planet has existed. The object itself is receding, but its light is still finding us. And in a very real, very profound sense, that means something from TON 618 has already arrived. Not matter, not gravity, not any kind of physical influence that could affect the Earth or its orbit, or the safety of anything living on it. But information, this is what light carries across cosmic distances. Not danger, not threat. Information. Encoded in the wavelengths of each photon is a record, a snapshot of conditions at the source, when the light was emitted. The temperature of the accretion disk, the velocity of the material spiralling inward, the mass of the black hole generating the gravitational field, the distance the light has travelled, written into the degree of redshift measured, when the photon finally arrives. All of that information has been crossing the universe for 10 billion years, packaged in particles of light, moving at the only speed they are capable of, aimed at nothing in particular, and yet arriving here. Now, in devices designed specifically to capture them. and extract the story they carry. So when we ask whether Ton 16 is coming toward us, the answer depends entirely on what we mean by it. The black hole itself? No. Absolutely not. It is receding and will continue to recede for as long as the universe continues expanding. But the light, the ancient message encoded in photons, that left that object when the cosmos was still young? Yes. That is arriving. That has been arriving. For as long as we have had telescopes sensitive enough to detect it. And it will continue arriving. For as long as we keep looking in that direction. There is something almost poetic about this arrangement. The universe expanding in one direction, carrying objects farther apart. And light travelling in the other direction, closing the informational gap. Even as the physical gap widens. Two processes moving in opposition, neither able to fully overcome the other. We will never visit Ton 618. Even travelling at the speed of light, which no object with mass can do. The journey would take over 10 billion years one way. By the time we arrived, the universe would be unrecognisably different. Our sun would be long dead. The Milky Way and Andromeda galaxies would have collided and merged. The stars we navigate by would have exhausted their fuel and faded into darkness. And even if we could somehow make that journey, we would not be travelling toward the Ton 618 we observe in our telescopes. We would be travelling toward whatever it has become. In the billions of years since the light we see tonight was emitted, a different object entirely. Possibly quieter, possibly larger, possibly surrounded by a galaxy. Reshaped by billions of years of evolution we cannot predict. The version of Ton 619 captured in the light reaching us now is a moment frozen in the deep past. A photograph from an era when the universe was fundamentally different. When galaxies were younger. When the large-scale structure of cosmic filaments and voids was still assembling itself. When the rules governing how black holes grow were being written in real time by processes we still do not fully understand. So should we be worried about Ton 618? No, not in any practical sense, not in any way that should disturb sleep, or generate anxiety, or suggest that something dangerous is approaching. The object poses no threat. The expansion of the universe guarantees that. But should we be paying attention to it? Yes, absolutely, because the light arriving from Ton 618 every night is not just data, it is evidence, hard, measurable, photographic evidence, that the early universe was capable of building structures our current models struggle to explain, that the cosmos operates on scales and timescales that dwarf anything in our daily experience, that the rules we have written down to describe how mass and gravity and time interact are incomplete at the edges of what we can observe. Ton 618 is not coming for us, but its light has been travelling toward us since before we existed. And in the deepest sense, that is more profound than any physical approach could ever be. The message is already here, we are still learning how to read it. There is something quietly extraordinary about the light from distant objects. Not the objects themselves. The light. The photons. The individual particles of electromagnetic radiation that began their journeys billions of years ago, and are only now, at this exact moment, completing the crossing. When you look at Ton 618 through a telescope, you are not seeing the object as it exists right now in the present moment of the universe. You cannot. The distance is too great. The speed of light, while extraordinary by human standards, is still finite, still limited, and the gap between here and there is measured not in miles or kilometres, but in something far more profound. Time itself. The light you observe tonight left Tion 618, approximately 10.4 billion years ago. Let that settle for a moment. Not as a number on a page, as a span of history, a duration so immense that almost nothing familiar to you existed when that journey began. 10.4 billion years ago, the universe was young. Not infant, it had already existed for over 3 billion years by that point, but young in the sense that most of the structures we consider fundamental were still forming. Galaxies were smaller, denser, more chaotic. The rate of star formation across the cosmos was far higher than it is today. The space between galaxies had not yet expanded to the vast, quiet voids we see in the present universe. Earth did not exist, not in any form, not as a planet, not as a cloud of dust orbiting a young star, not even as the raw material waiting to coalesce. The region of space where our solar system would eventually form was simply part of a larger molecular cloud, drifting through the outer arms of a galaxy that would one day be called the Milky Way. Our sun had not ignited. The hydrogen and helium and trace heavier elements that would eventually collapse under gravity to form it were still scattered across light years of space, diffuse and unorganized, showing no sign of the structure they would become. There was no rock that would become Earth, no ocean, no atmosphere, no amino acids assembling themselves into the first fragile structures that might be called alive. None of it existed yet, and into that empty, unformed region of space, a place that meant nothing to the universe at large, a single photon of light began travelling. It did not know where it was going. Photons do not navigate. They do not aim. They simply move in straight lines. At the only speed they are capable of, carrying energy outward from whatever event produced them, until something absorbs them or redirects them. This particular photon had been emitted from the accretion disk surrounding Ton 618, one among trillions upon trillions, radiating outward in every direction. Most would travel forever into empty space, never encountering anything significant enough to stop them. A tiny fraction would, by pure chance, be aimed toward a patch of the universe, where billions of years later a small planet would form, and a curious species would build devices capable of capturing ancient light. The photon began its journey through a universe that was smaller and denser than the one we inhabit now. As it travelled, the universe expanded around it, not into anything, not outward from a centre. Space itself stretched, carrying galaxies away from each other, increasing the distances between all objects, not bound together by gravity. And as space stretched, so did the wavelength of the photon. This is what astronomers call redshift. Light emitted at a particular wavelength, say in the blue or ultraviolet range, gets stretched as it crosses expanding space. By the time it arrives at a distant telescope, billions of years later, its wavelength has shifted toward the red end of the spectrum. The more the universe has expanded during the photon's journey, the more dramatic the shift. This is how we measure cosmic distances. Not with rulers, with light itself. By measuring how much a photon's wavelength has been stretched, we can calculate how long it has been travelling, and therefore how far away its source must be. The light from Ton 619 shows a redshift, corresponding to a journey of just over 10 billion years. 10 billion years of travel through galaxies and voids, past other quasars and colliding galaxies, and regions where new stars were igniting and old stars were dying. Most of the photons emitted from Ton 619 during that ancient era never made it this far. They were absorbed by clouds of gas. scattered by dust, redirected by gravitational lensing, around massive objects along the way. But a few survived, and slowly, across that unimaginable span of time, something changed in the destination. The molecular cloud in the outer Milky Way began to collapse. Gravity pulled hydrogen together. The core grew denser and hotter. Nuclear fusion ignited. A star was born. Our Sun. Approximately 4.6 billion years ago, roughly halfway through the photon's journey, the star that would one day warm a planet, capable of observing distant light, came into existence. Around that young star, a disk of gas and dust began to flatten and coalesce. Rocky material accumulated in the inner regions. Larger bodies formed through collision and accretion. One of those bodies, orbiting at just the right distance from the new star, grew large enough to hold an atmosphere and began to cool. Earth formed. Volcanoes reshaped its surface. Water vapor condensed into oceans. Chemistry became biology. Single cells became complex organisms. Life diversified across billions of years. Continents shifted. Ice ages came and went. Species emerged and vanished. And still the photon travelled. It crossed the halfway point of its journey. Around the time the first simple cells appeared in Earth's oceans, it passed the 3/4 mark. Somewhere around the time multicellular life began to diversify, it entered the final billion years of travel, as plants colonized the land and animals followed. By the time it crossed into our local region of the universe, dinosaurs had risen and fallen. Mammals had spread across every continent. A particular lineage of primates had developed language, tools, agriculture, writing, mathematics, and the scientific method. And one night, perhaps last month, perhaps last year, perhaps this very evening, that photon completed the final stage of its 10 billion year crossing and struck a mirror on a mountaintop telescope, on the third planet orbiting an unremarkable yellow star. It was captured, measured, analysed, catalogued, its wavelength recorded, its energy calculated, its story traced backward across time, to the moment it left the glowing accretion disk, of the largest confirmed black hole in the observable universe. This is what it means to observe something 10 billion light-years away. You are not looking at a distant place. You are looking at a distant time. The light arriving tonight is a messenger, from an era when the universe was barely a third of its current age, when galaxies were younger and stranger, when the rules governing structure formation were still being written in real time by the collapse of gas and the merging of black holes. TON 618 as it exists right now, in the present moment, wherever that moment is, in the local time of a galaxy 10 billion light-years away, is something no human will ever see. The light carrying information about that present version has not yet travelled far enough to reach us. It will not arrive for another 10 billion years, long after our sun has exhausted its fuel and expanded into a red giant, long after Earth has been consumed or rendered lifeless. What we see as a ghost, a preserved image from the deep past, frozen in the light that has spent more than half the age of the universe travelling toward us, and every clear night more photons arrive, each one slightly younger than the last, by fractions of a second, by minutes, by hours, but all of them ancient beyond any human sense of time, all of them carrying the same information, encoded in their wavelengths and energy levels, all of them completing journeys that began when nothing familiar existed, and ending their travels in the mirrors and sensors of devices built by a species, That has existed for less than 1% of 1% of the time those photons have been in motion. The light is still finding us. It has been finding us. Since we first pointed telescopes at that patch of sky, it will continue finding us for as long as we keep looking. And each photon that completes the crossing carries the same quiet message from an object that should not have existed when it did, built by a universe that was doing things our models still cannot fully explain. The message is simple. I was here. I was enormous. I was already ancient when this light left me. And I am still out there. Sometimes the most extraordinary things are found by accident, not because anyone was searching for them specifically, not because instruments were aimed at a particular target, with clear expectations of what might be revealed, but because someone was simply looking, cataloguing, recording what was there, without yet knowing what any of it meant. This is how TON 618 entered human awareness, not with fanfare, not with a sudden realization that something unprecedented had been observed, but quietly as a faint blue mark on a photographic plate recorded during a routine sky survey in the 1950s, and filed away among thousands of similar marks that all looked unremarkable at the time. The year was 1957. The place was the Tonantzintla Observatory, located in the state of Puebla, Mexico, roughly 80 miles southeast of Mexico City. The observatory had been conducting a systematic survey of the sky, photographing large sections of it, using sensitive plates capable of capturing faint objects, invisible to the naked eye. The goal was simple: document what was out there, build a catalogue, create a reference that future astronomers could return to when better instruments and better understanding became available. One of those photographic plates captured a small, faint bluish object. It was logged, given an identifier based on the observatory name and its position in the catalogue. TON for Tonantzintla. 618 because it was the 618th entry on the list. And then it sat there, unremarked, unexamined in any detail, just another data point, in a sky full of data points. Nobody thought much of it at the time, because there was no reason to. The object looked like a star. Faint, yes. Distant, probably, but visually indistinguishable from countless other point sources. Scattered across the night sky, without additional information, spectra, redshift measurements, luminosity calculations, there was no way to know it was anything other than what it appeared to be. For 15 years, that is all it remained. A catalogue entry. A small mark on old photographic paper stored in an archive, its true nature hidden behind the limits of the instruments. That had first detected it. But slowly, technology improved. By the early 1970s, astronomers had access to far more sophisticated spectrographs, devices capable of splitting an object's light into its component wavelengths with remarkable precision. These instruments could reveal not just the brightness of a distant object, but its composition, its temperature, its motion relative to Earth, and most importantly, its distance. When improved spectrographs were finally turned toward TON 618, what they revealed was startling. The object was not a star. The spectrum showed something entirely different. The light was heavily redshifted, stretched toward longer wavelengths in a way that indicated either enormous velocity or enormous distance. When astronomers calculated what that redshift implied, the numbers were striking. The light had been travelling for over 10 billion years. The object was not located in our galaxy, or even in a nearby galaxy. It was situated in the distant universe, in an era when the cosmos itself, was less than a third of its current age. And the characteristics of the light, the specific wavelengths present, the intensity, the way energy was distributed across the spectrum, matched the signature of something called a quasar. Quasars were not completely unknown by the 1970s. The first one had been identified roughly a decade earlier, in 1963, when astronomer Martin Schmidt measured the redshift of an object called 3C273, and realized it was far more distant than anyone had expected. The term quasar, short for quasi-stellar radio source, later broadened to quasi-stellar object, was coined to describe these strange star-like points of light that were actually the intensely bright cores of very distant galaxies. But even among quasars, TON 618 was unusual. The redshift placed it at a distance of approximately 10.4 billion light-years. The luminosity required to appear as bright as it did from that distance was staggering, when astronomers calculated the energy output necessary. To produce the observed brightness, the numbers pointed towards something far larger than most known quasars. This was not just another entry in a growing catalogue of distant objects. This was something at the extreme end of what the universe seemed capable of building, and that realization changed the context of everything that had been sitting quietly in the archive since 1957. The faint blue speck on the photographic plate was suddenly one of the most luminous objects ever observed. The unremarkable catalogue entry was now a window into the early universe, into an era of galactic evolution that was just beginning to be understood. The object that nobody had paid attention to for 15 years was now demanding attention, not because it had changed, but because our ability to understand what we were looking at had finally caught up. This is one of the quiet truths about astronomical discovery. The universe does not reveal itself all at once. It waits. The light is always there, crossing the darkness, arriving at our telescopes whether we understand it or not. But meaning only emerges when the instruments and the knowledge and the questions align in the right way. TON 618 had been visible since the moment its light entered our local region of space. It had been photographed in 1957. But it was not truly discovered, not truly understood as something extraordinary, until the technology existed to measure what that light actually meant. The revised understanding of TON 618 came in stages. First, the recognition that it was a quasar, then measurements refining its distance and luminosity, then calculations estimating the mass of the central black hole, required to produce that level of energy output. Each new measurement added detail to the picture. Each refinement pushed the scale upward. By the time modern instruments and computational models were applied to the problem, the estimates had settled into a range that was difficult to reconcile with existing models of black hole growth, somewhere between 40 and 66 billion solar masses, an event horizon spanning roughly 2,600 astronomical units, a luminosity of approximately 140 trillion times that of our Sun, an age corresponding to a universe less than 4 billion years old. These were not approximate figures subject to large uncertainties. They were constrained by multiple independent lines of evidence: redshift measurements, brightness observations, spectral analysis, gravitational modelling. The margins of error were significant in absolute terms, but they did not change the fundamental conclusion. TON 618 was the largest confirmed black hole humanity had ever found, and it existed at a time when our models said it should not yet have been able to grow that large. The discovery reshaped what astronomers thought was possible. in the early universe. Before TON 618, supermassive black holes, in the range of a few million to perhaps a few billion solar masses, were considered extreme but understandable. The growth mechanisms, accretion, mergers, gradual accumulation over billions of years seemed sufficient to explain them. TON 618 forced a reconsideration of those assumptions. If something this large could exist, less than 4 billion years after the Big Bang, then either black holes grew much faster in the early universe than current models predicted, or they started from much larger seeds than stellar collapse alone could provide, or both. The object sitting quietly in the Tonant-Sintler catalogue since 1957 had become a test case, a benchmark against which theories of cosmic evolution had to be measured, and most of those theories were found wanting, not entirely wrong, just incomplete, missing something about the conditions and processes that operated in the infant cosmos, something that allowed structures of this scale to assemble far more quickly than the equations suggested they should. And here is what makes this story particularly resonant. TON 618 was not found because someone went looking for the largest black hole in the universe. It was found because someone pointed a telescope at the sky and recorded what was there, because someone catalogued a faint blue speck without knowing what it was, because someone years later returned to that old data with better tools and asked better questions. The discovery was not dramatic. It was patient, incremental, built on decades of work by people who never saw the final picture, but contributed pieces to it nonetheless. This is how most astronomical discoveries actually happen, not in sudden flashes of insight, but in the slow accumulation of evidence, in old photographs revisited, in catalogues re-examined, in questions asked about objects that were always there, waiting quietly for the right instruments, and the right moment to reveal what they actually were. TON 618 waited 15 years between being photographed and being understood, and it has been waiting 10 billion years between emitting the light we see and receiving any acknowledgement that the message finally arrived. The universe is patient, and sometimes so is discovery. For decades, TON 618 held a unique position in our understanding of the cosmos. It was the largest confirmed black hole, the most luminous single object ever observed, the most dramatic example of something that should not have existed in the early universe, but clearly did. It sat alone at the extreme edge of what we thought was possible. A record holder and a puzzle all at once. But records, by their nature, are made to be broken, or in this case, discovered to have never been alone in the first place. In late 2021, a new space telescope began operations. The James Webb Space Telescope, named after a former administrator of NASA, launched on Christmas Day 2021 after more than 2 decades of development and refinement. It was designed to observe the universe in infrared wavelengths, light invisible to human eyes but carrying information about distant, faint, and extremely old objects that visible light telescopes struggle to detect. One of its primary scientific goals was to look back toward the earliest galaxies, to peer into the era when the first stars were igniting, when the first galaxies were assembling themselves from clouds of primordial gas, when the large-scale structure of the universe was just beginning to take shape. What astronomers hoped to find was instructive. What they actually found was unsettling in ways that echoed the original discovery of TON 618. The James Webb observations revealed something unexpected. The universe in its infancy, in the first few 100 million years after the Big Bang, was populated with galaxies far more mature, far more structurally complex, and far more luminous than models had predicted. More surprisingly still, many of these galaxies harboured active supermassive black holes, already grown to millions or billions of solar masses, already feeding on vast quantities of material, already shaping their host galaxies through powerful jets and radiation. And these black holes existed in galaxies so young that their very presence was theoretically inconvenient. Astronomers began calling these objects the little red dots, a name born from the way they appeared in infrared observations, small faint points of light that appeared reddish due to the extreme redshift of their light after travelling through an expanding universe. But appearances were deceiving. The little red dots were extraordinarily luminous, and the faint appearance was a direct result of their distance and the universe's expansion, not an indication of their actual power. Some of these objects turned out to be active supermassive black holes already grown to billions of solar masses in a cosmos only a few 100 million years old. A few 100 million years. The problem this created was immediate and profound. The timescale was even tighter than it had been for TON 618. If TON 618 at 10.4 billion light-years represented a black hole that had grown impossibly large in the first 4 billion years of cosmic history, these new discoveries represented black holes that had grown impossibly large in less than a tenth of that time. The equations that described black hole growth through accretion and mergers, equations that had been carefully calibrated and tested against decades of observations, suddenly looked fundamentally incomplete. Not just at the extreme edges, but at the very beginning. Something in the early universe was enabling the rapid assembly of black holes on scales that should have been impossible. And it was not just TL1 618. It was potentially a widespread phenomenon, a systematic feature of the infant cosmos rather than a rare and anomalous outlier. The deeper James Webb looked, the more examples it found. This is where the story takes on a different character than the discovery of TON 618 itself. TON 618 was strange, unexplained, but it was also singular, the largest of its kind, the most extreme example. It was possible to imagine it as a rare event, an unusual circumstance, something that had happened once under particularly favourable conditions. But the James Webb discoveries suggested something more systemic, that the early universe was not the slow, patient builder we had assumed, that it was capable of constructing extreme structures, supermassive black holes, massive galaxies, at a pace that contradicted our models. That somewhere in the first few 100 million years of cosmic history, processes were operating that our current understanding simply does not account for. And if those processes existed, if the early universe could build black holes this quickly and this large, then T1 618 was not unique. It was simply the largest example we had confirmed so far. A record holder, yes, but part of a broader pattern rather than an isolated anomaly. The implications of this realization are still rippling through the astronomical community. Entire models of cosmic evolution are being reconsidered. Papers are being written proposing new mechanisms for rapid black hole growth. Observations are being planned to search for even larger black holes in even younger galaxies. The fundamental question underlying it all is simple but profound. What did the early universe know about assembling massive structures that our equations do not yet capture? Some astronomers have proposed that the early universe was far more turbulent, far more violent, far more chaotic than we had believed. That the first galaxies were collision-prone environments where black holes merged frequently and rapidly in environments that enhanced rather than suppressed their growth. Others suggest that the seeds from which these black holes grew were themselves much larger than stellar mass black holes, either from direct collapse of primordial gas clouds or from primordial black holes formed in the first moments after the Big Bang. If the seeds were larger, the subsequent growth, while still rapid, becomes slightly more plausible. Still others propose entirely new physics operating in the early universe, physics that only functioned under the extreme conditions of the infant cosmos, physics that has since become irrelevant as the universe expanded and cooled and settled into the more predictable patterns we observe today. None of these explanations are entirely satisfying. None of them fully close the gap between what our models predict and what we observe. But each one represents an attempt to expand our understanding in the direction the universe is pushing us. What is particularly striking about this story is the timing. TON 618 was discovered in the 1970s. It sat as a puzzle, a record, an unexplained extreme for nearly 50 years. Astronomers noted it, studied it, included it in papers, but it remained isolated, the most extreme example of its kind perhaps, but also the only example quite that extreme. Then James Webb launched, and suddenly the sky filled with similar objects, not identical, not all as large as TON 618, but similar in the fundamental way that mattered. They were too large for their age. The universe in its infancy had built them too quickly. TON 618 was not unique. It was simply the most extreme example of a widespread phenomenon we had been unable to see until our instruments became sensitive enough to detect the full population. This is a reminder of something important about science and observation. The universe does not change. But our ability to see it does. An object that seemed to be a singular puzzle piece for 50 years suddenly makes sense when we finally have the context to place it within. What looked like an anomaly becomes evidence of a pattern. What seemed impossible becomes merely improbable, and improbable becomes routine. And somewhere in the darkness between galaxies, TON 618 continues feeding. Consuming stars, radiating energy, sending its light outward, indifferent to the fact that the small species 10 billion light-years away has finally begun to understand that it is not alone. That others like it, or at least others approaching its scale, existed in the early universe as well. The record it holds may not stand forever. James Webb continues to observe. Deeper surveys continue to be planned. Each observation brings the possibility of finding something even larger, even older, even more extreme. But for now, TON 618 remains the most massive confirmed black hole in the observable universe. A record holder, a puzzle piece, an old photograph on a dusty shelf that suddenly, after billions of years of patient waiting, finally found its context. And in finding that context, it revealed that the early universe was building monuments, far grander than we ever imagined. There is a particular kind of humility that comes from truly understanding distance, not the abstract mathematical kind, not numbers on a page, but the felt, immediate, almost physical understanding of what it means for something to be so far away that the very concept of reaching it becomes almost meaningless, where the journey would consume more time than civilizations have existed, where the destination would be unrecognizably different by the time you arrived. This is the distance to TON 618. Imagine for a moment that we could build a spacecraft, the most advanced, most perfectly engineered machine ever conceived. A vessel capable of travelling at the speed of light itself, something physics tells us is impossible for any object with mass. But let us imagine it anyway. A ship moving at 186,000 miles per second, the fastest speed the universe permits. A one-way journey to TON 618 at that speed would take more than 10 billion years. More than the entire age of the Earth. more than the entire span of human civilization multiplied by 100,000, more than any meaningful timescale, that our species understands or can relate to, and that assumes we could somehow achieve the speed of light itself. In reality, any spacecraft we could build, any propulsion system we could develop within the constraints of known physics, would travel far more slowly. A journey that might take centuries with advanced technology instead becomes a journey that takes billions of years. The destination stops being a place we could ever reach. It becomes, in any practical sense, unreachable. But the distance is only the beginning of the problem. Even if we could somehow suspend the laws of physics and make the journey, we would not be travelling toward the Ton 6 Betaine we observe in our telescopes. We would be travelling towards something entirely different. The light we see tonight left Ton 619 over 10 billion years ago. In the time since that light was emitted, the black hole has continued to feed, continued to grow, continued to evolve. The version of it existing in the present moment of the universe, wherever that moment is in the local time of its distant galaxy, is not the version captured in the light reaching us now. It is an older version, an ancient version, a record of what Ton 618 was, not what it is. When that ancient light was being emitted, the black hole was already enormous, but it has had 10 billion more years to feed since then. 10 billion more years to consume stars and dust and gas. 10 billion more years to merge with other black holes, to grow heavier, to reshape its surroundings. What we would find if we could somehow arrive at Ton 6's current location would be something we could never have predicted. From the light, now, reaching us, we would be travelling toward a future version of the object, separated from us not just by distance, but by billions of years of evolution we cannot observe directly. And there is another layer to this problem, a layer that touches on one of the deepest limitations of what science can ever achieve. We cannot send probes to Ton 6. We cannot build instruments capable of travelling that distance and returning data. We cannot conduct experiments. We cannot take samples. We cannot do any of the things that science normally relies on to gather information about distant phenomena. All we have are photons, ancient light, particles of electromagnetic radiation that have travelled farther and longer than anything else we can observe, carrying encoded within their wavelengths and energy levels a record of conditions at the moment they were emitted. We can measure those wavelengths. We can analyse the spectrum. We can extract information about temperature, density, composition, motion, distance. But we are confined entirely to what those photons tell us. We cannot ask follow-up questions. We cannot conduct targeted observations of specific features we find interesting. We cannot zoom in on something puzzling and examine it more closely in a different wavelength, or through a different instrument. We can only receive the message the universe has chosen to send. This is a profound constraint on human knowledge, not just with Ton 16, with everything beyond a certain distance. The farther away an object is, the older the light reaching us becomes, and the less freedom we have to choose what we observe. We are confined to observing what happens to reach us by chance, what happens to be bright enough to detect, what happens to emit light in wavelengths our instruments are sensitive to. The universe is not obligated to show us the things we most want to understand. It shows us what it shows us, and we work with that. For Ton 618, the light that reaches us tells us quite a lot. The redshift tells us the distance. The brightness tells us something about the energy output. The spectrum tells us about the composition and temperature of the accretion disk, the way the light varies over time. tells us something about the structure of the emitting region. From all of that, we can piece together a picture, not a complete picture, not a picture with perfect clarity, but a picture nonetheless, enough to understand that something extraordinary is happening. 10 billion light years away, enough to recognize that our models do not fully account for it, enough to know that we are missing something important about how the universe builds its largest structures. But we will never know the complete picture. We will never visit TON 618. We will never conduct an experiment there. We will never see it in real time, as it exists in the present moment. All we will ever have is light. And that, in a strange way, is both a profound limitation and a profound gift. It is a limitation because we are constrained, because our knowledge is incomplete, because there are questions we cannot answer, mysteries we cannot fully resolve, details we will never access. The universe keeps its deepest secrets behind a wall of distance and time that no spacecraft will ever cross. But it is also a gift because that light is enough. It is enough to reach across 10 billion years of cosmic history and carry us information from an era when the universe was young and strange and building things that still confuse our best scientists. It is enough to show us that we do not live in a universe we have completely understood. It is enough to humble us, to remind us that the cosmos is far larger and stranger and more complex than any human theory yet devised. The photographs of TON 618 captured by our telescopes tonight will be replaced tomorrow by slightly newer photographs. Each image captures light slightly more recent than the image before it, by fractions of a second, by minutes, by hours. With each new observation, we pull a thread, and the thread keeps getting longer, extending back through time toward a source we will never see in its present state. Whatever waits at the other end of that thread, whatever TON 618 has become in the billions of years, since the light now reaching us was emitted, will remain forever beyond our reach, a future we cannot observe, a present we cannot access, a version of the object that exists somewhere in the expanding universe but never in the telescopes we point at the sky. We observe the ghost of what it was, we wonder about what it is, and we accept that some things in the cosmos will always remain just beyond the edge of what we can know, not because of any failure of science, but because of the way the universe itself is constructed. Space is too vast, time is too long, light travels too slowly, and we are too small and too short-lived to bridge the gap. TON 618 will keep its deepest secrets, and all we can do is listen to the ancient light that keeps arriving, carrying pieces of a story we are still learning how to read. There is a particular quality to the silence of a clear night, not an absence of sound exactly, but a kind of stillness, a quietness that settles over things, when most of the world has stopped its daytime activity, and the air itself seems to hold its breath. On such nights, if you find yourself far from city lights, you can see the Milky Way stretching across the sky. In all its pale, luminous glory, hundreds of billions of stars scattered across an incomprehensible distance, each one burning in its own private silence, each one utterly indifferent to the small creatures. Looking up at them from a small rocky planet, and somewhere in the darkness beyond those familiar stars, where no human eye can see without technological assistance, light is still arriving. Every night, without fail, through clouds and clear skies alike, though only detected on clear nights. When sensitive instruments point in the right direction, light that has been travelling since before the Earth existed, completing the final stage of a 10 billion year journey. To strike mirrors and sensors on mountaintops, scattered across this planet. The light from TON 617, each photon that completes this crossing, carries the same message encoded in its wavelength and energy. I was here, I was enormous, I was already ancient when this light left me, and I have been growing ever since. The message is not written in words, there is no audible voice, but the information is there nonetheless, readable by instruments designed to extract meaning. From the subtle properties of electromagnetic radiation, scientists spend their careers learning to translate what light tells us, learning to read the story each photon carries, and the story TON 618 tells is one of extremes. Consider what it means, in concrete terms, to be observing something 10 billion light-years away. The Milky Way, our home galaxy, contains somewhere around 400 billion stars. Every constellation you have ever seen, every star visible to the naked eye on the darkest night, Polaris, the North Star, Sirius, the brightest star in the sky, the entire river of light stretching across summer skies, all of it, the combined light of 400 billion suns, represents the total output of an entire galaxy. TON 618, a single object at the centre of a single distant galaxy, outshines that entire galaxy by a factor of several thousand. One black hole, one accretion disk, one feeding engine of incomprehensible violence and energy, more luminous than 400 billion stars combined, more luminous than thousands of galaxies. The light from that single point brighter than entire cosmic cities housing trillions of suns, and that is what we see from 10 billion light-years away. After the light has been stretched by the expansion of space, after most of the photons have been lost or scattered or absorbed along the way, after 10 billion years of travel has dimmed it, to the point where it registers as merely a faint speck in our telescopes. What TON 618 was emitting at full strength before any of that attenuation is almost impossible to conceptualize. And this is where the message becomes something more than mere data. Every night, when that light completes its crossing and lands in a detector somewhere on Earth, it is carrying a record from an era when the universe was fundamentally different, a time when galaxies were closer together, denser, more chaotic, when star formation was happening at rates 1,000 times higher than it is today, when the large-scale structure of the cosmos was still assembling itself, when the rules governing what structures could form and how quickly they could grow were still being written in real time. The light arrives carrying information about that era, about conditions in the early cosmos, about what was possible, about what the universe was building when it was young. And alongside that scientific information comes something else, something harder to quantify but no less real. A perspective, a context for understanding our own place in the cosmos. Imagine standing on Earth at night and looking up at the Milky Way. It is large, it is beautiful, it seems to fill the sky, hundreds of billions of stars, most of them invisible individually, but collectively creating that pale river of light, stretching from horizon to horizon. It is the vista that has inspired humans. For all of recorded history, the canvas against which we have painted our stories and myths, the scale against which we have measured our own significance and found ourselves wanting. Now imagine stepping outside that galaxy, turning around and looking back at it from a vast distance, from the perspective of another galaxy 10 billion light-years away, from a vantage point in the early universe. From that viewpoint, the Milky Way would still be large, still impressive by most standards. Hundreds of billions of stars, arms of gas and dust, a structure recognizable as a major galaxy. But from the position of TON 618's host galaxy, sitting at that viewpoint, the Milky Way would appear as what it actually is. One galaxy among billions, significant only because we happen to live in it, unremarkable by cosmic standards. And TON 618, that single point of light at the centre of its galaxy, would be far more luminous than the entire Milky Way, more powerful, more visible, more significant as a single object than our entire home galaxy as a whole. Every civilization that has ever existed, every human life that has ever been lived, every love story, every war, every discovery, every dream, all of it contained within the boundaries of the Milky Way, compressed into that single, relatively modest spiral of starlight. Outshone from the perspective of the early universe by the glow of a single feeding black hole, this is what the arriving light shows us when we have the courage to look at it directly. Not danger, not threat, but perspective. A cosmic context that reshapes how we think about ourselves and our significance. A reminder that the universe is far larger than human history, that our species is not the measure of all things, that the cosmos builds structures and performs processes that dwarf anything we have accomplished or even imagined. And somewhere in the present moment, a present we cannot observe, cannot reach, cannot access. TON 618 continues, still feeding, still radiating energy, still sending light forward into an expanding universe. The version of it existing right now has grown even larger than the version. Captured in the light reaching us tonight, it has consumed more stars, merged with other black holes perhaps, continued the patient, ancient process of accumulating mass at the centre of its galaxy. We will never see that present version. The light carrying information about it will not reach us for billions of years more. By that time, our sun will have expanded and consumed the inner planets. Earth will be a cinder orbiting a dying star. The entire solar system will be approaching the end of its story. But the light will still be arriving, still completing its journey, still carrying the same message. I was here. I was enormous.
I am still here, still growing, still sending. This is what it means to receive light from the distant universe.
To be receiving messages from a time before you existed. Messages that have travelled longer than your entire species has existed. Messages that will continue arriving long after everyone alive today has turned to dust. Messages from objects that are themselves older and stranger and more powerful than anything in our direct experience. Every photon that arrives is a connection across time, a thread linking us to an era that might as well be mythological in how distant it seems. A whisper from the infant cosmos, reaching across billions of years to find us. And we are listening. Not with our ears, but with instruments designed to hear what light has to say. With mathematics that can translate wavelengths into stories. With patience and curiosity. And the humble recognition that the universe is showing us something that matters. Something that changes how we understand ourselves. The message is still arriving every night, and in the deepest sense, we are still learning how to read it. There is a particular quality to the wonder that comes from understanding your own smallness. Not the fear that sometimes accompanies it, not the anxiety or the vertigo that can come from contemplating scales too large to fully grasp, but something gentler than that, something quieter, a kind of peaceful acceptance that the universe is far larger and stranger and more complex than any human theory has yet managed to capture. This is what TON 618 teaches us, if we sit with it long enough. Not danger, not threat, but wonder. The existence of TON 618 tells us three simple things that reshape how we understand the cosmos. The first is this: you do not know how big things can get. We have equations, we have models, we have predictions based on billions of hours of computation and observation, and yet, the universe builds structures that exceed those predictions, not by a little, by a lot, by factors that force us to fundamentally reconsider what is possible. A black hole with 66 billion solar masses, an event horizon spanning 2,600 astronomical units, a luminosity of 140 trillion suns. These are not theoretical extrapolations from smaller examples. These are measured realities, confirmed observations of objects that exist in the universe right now, feeding and growing and reshaping their surroundings on scales that dwarf anything in our solar neighbourhood. And TON 618 may not even be the largest. Somewhere out in the archives of telescope data, in old photographic plates, in digital surveys, in images yet to be analysed, there are probably larger ones, or objects waiting to be discovered, waiting for the right astronomer to notice them and ask the right questions. The universe, it seems, has built its monsters larger than we initially dared imagine. The second thing TON 618 teaches us is this: you do not know how fast they can grow. The early universe was not the slow, patient place our models assumed it to be. It was a place where extreme structures assembled at speeds that contradict our equations, where black holes grew to billions of solar masses in the space of a few billion years instead of the tens of billions our accretion models predicted. Something about those early conditions, the density, the chaos, the specific mechanisms available, allowed for growth rates we still do not fully understand. Direct collapse perhaps, runaway mergers. Primordial black holes formed in the first moments of existence, or something we have not yet considered, some process operating only under the extreme conditions of the infant cosmos. But whatever it was, the universe was building its larger structures far faster than we thought possible, and if we do not fully understand how the early universe built TON 618, how can we claim to understand the universe at all? The third thing is perhaps the deepest. You do not know how much of the universe is still hidden from you. We have built telescopes that reach back to within a few 100 million years of the Big Bang. We have catalogued hundreds of billions of galaxies. We have mapped the large-scale structure of the cosmos across billions of light years. We have developed mathematical frameworks that describe how gravity, space and time interact, and yet TON 618 reminds us that vast regions of understanding remain unmapped. There are black holes we have not yet discovered, processes we have not yet identified, mechanisms operating in the early universe that our current equations do not capture, whole layers of cosmic evolution that we are only just beginning to understand because our instruments have finally become sensitive enough to see them. The James Webb Space Telescope found little red dots, supermassive black holes in galaxies so young that their existence was theoretically inconvenient. What else is out there? What other discoveries are waiting in the data we have not yet analysed carefully enough? What structures are hiding just beyond the edge of what our current telescopes can detect? The universe is keeping secrets, large ones, and TON 618 is just the most dramatic example we have found so far. And here is the thing that makes this genuinely comforting rather than frightening. These unknowns do not need to terrify us. We are not in danger from TON 618. We are not threatened by the early universe's ability to build large structures. The expansion of space guarantees that we will never grow closer to these cosmic monsters. Gravity does not work like a cosmic net that suddenly activates and pulls us in. But not being in danger does not mean not paying attention. The fact that we do not fully understand how TON 618 came to be is not a failure. It is an invitation. An invitation to deeper thinking, to revised models, to new questions asked with humility and care, to the recognition that science is not a finished product, but an ongoing conversation between humans and the universe they inhabit. TON 618 is not frightening because it is heading toward us. It is profound because it reminds us that the universe operates on scales and timescales, and with mechanisms that our best minds are still struggling to fully comprehend. Because it shows us, in stark, measurable terms, the limits of what we know. Every time we observe TON 618, we are pulling a thread, and the thread keeps getting longer. It extends back through 10 billion years of cosmic history. It connects us to an era when everything was different, when the rules were still being written, when the universe was doing things that our equations still cannot fully account for. Whatever waits at the other end of that thread, in the present moment of TON 618's existence, in its current state after 10 billion more years of feeding, will remain forever beyond our direct knowledge. A mystery, a future we cannot see, a present we cannot access, and that is okay. Because mystery is not the opposite of understanding, it is the foundation of it. Every answered question reveals new questions. Every measurement taken at greater precision reveals new subtleties. Every model built to explain the universe is always incomplete, because the universe is always larger than the models we build. TON 618 sits at the edge of what we know and understand. It is a landmark on the boundary between mapped and unmapped territory, and landmarks like this are precious. They are not failures of our knowledge. They are guides toward what we need to learn next. Somewhere in the darkness between galaxies, TON 618 continues its patient work, consuming stars, radiating energy, sending its light outward toward a cosmos that is slowly learning to see it more clearly. And on this small blue planet, orbiting an average star in an average galaxy, a species that has existed for less than 1% of 1% of the time that TON 618 has been feeding, looks up at the night sky and begins, slowly, to understand. We are small. The universe is large. And that is not something to fear. It is something to wonder at. Let us return for a moment to where we began. You are floating, not falling, not drifting in any direction that feels dangerous, simply floating. Suspended in the quiet between the stars, in the kind of silence that has no edges, no walls, no floor beneath you, and no ceiling above. But now, something has changed. The stars around you are no longer just beautiful points of light scattered randomly across darkness. Each one carries weight now. History. Each star you see is a sun like our sun, a furnace burning hydrogen into helium, radiating energy outward in all directions, waiting patiently for billions of years until its fuel runs out. Many of those stars have planets orbiting them. Some of those planets might harbour life. Most will not. But they are there nonetheless. Rocky worlds spinning in the darkness, each one unique, each one a universe unto itself. The Milky Way stretching overhead is no longer just a river of light. It is a home. A place where trillions of life forms exist right now. Where billions of civilizations might be looking up at their own night sky, asking the same questions we ask. Where consciousness, in forms we cannot imagine, is contemplating the same cosmos we are contemplating. And far beyond that familiar river of stars, beyond the edge of what your eyes can see, beyond even the farthest reaches of what telescopes can touch, TON 618 is still out there, still feeding, still growing, still sending its ancient light across the void. The journey we have taken together through these sections has been a journey inward, not toward Ton 618, that would be impossible, but inward, toward understanding, toward a deeper appreciation of how the cosmos is constructed, of what is possible at the extremes of size and scale and time, of what we know, and more importantly, of what we do not yet know. We have learned that the universe is far more complex than our equations initially suggested, that the early cosmos was building extreme structures at speeds that still confuse our best scientists. That light travelling across 10 billion years carries messages from an era we can never visit, telling stories we are only just beginning to learn how to read. We have learned that Ton 618 is not unique, that it is simply the largest confirmed example of a widespread phenomenon, that the early universe was populated with black holes, far larger than our models predicted, growing far faster than our equations said they should. That somewhere in the darkness, waiting to be discovered, there are probably even larger examples. But we have also learned something more fundamental. We have learned that not knowing is okay, that the existence of mysteries is not a failure of science. It is the foundation of science. Every question answered reveals new questions. Every measurement taken at greater precision reveals new subtleties. The universe is always larger than the models we build to describe it. Ton 618 sits at the edge of what we understand. It is a lighthouse marking the boundary between mapped and unmapped territory, and rather than being frightening, this is strangely comforting, because it means there is always more to learn, always more to discover, always another layer of mystery waiting to be unveiled. The universe will never run out of surprises for us, never become entirely comprehensible, never lose its capacity to humble us, and remind us of our smallness. So as you drift here among the stars, feeling the weight of all this knowledge settling into you, let the tension begin to ease. There is no danger coming. The expansion of the universe guarantees that Ton 618 will remain forever at a distance we will never close. There is no threat looming, only the quiet, patient existence of structures, larger and older and stranger than anything we have built or could build. The cosmos is vast, it is beautiful, it is largely incomprehensible. And that is exactly as it should be. Your heart is beating slowly now. Your breath is becoming shallow and easy. The stars around you are beginning to blur slightly at the edges, as if seen through water, or through the haze of approaching sleep. The silence is deeper now, more complete, the kind of silence that comes just before sleep claims you entirely, and somewhere 10 billion light years away, in a galaxy whose name we do not even know, Ton 618 continues its eternal work, consuming, radiating, growing, existing in a way that still partially defies our understanding, and sending its ancient light outward, patient and unhurried, knowing that it will take billions of years. To complete each journey, knowing that by the time it arrives at distant telescopes, it will be carrying information about a version of itself billions of years old. But the light keeps travelling anyway. The message keeps being sent, and somewhere on a small blue planet, a curious species keeps looking up and asking questions, keeps building better instruments, keeps slowly, patiently, learning to read what the universe is trying to tell them. You can rest here now, among the stars, in the quiet, in the gentle knowing that the cosmos is far larger than you, far stranger than you imagined, and far more beautiful than fear could ever touch. There are no monsters here, only wonder, only the vast, patient turning of galaxies, only light that has travelled for billions of years to reach you, carrying stories you are only beginning to understand. Let sleep come gently. Let the boundaries between waking and dreaming dissolve. Let yourself drift deeper into the darkness, knowing that darkness is not empty. It is full of light. Ancient light. Patient light. Light that has been travelling since before you existed, arriving now at this exact moment to tell you a story about a universe that is far more magnificent than any theory, any equation, any words could ever fully capture. Rest here, among the stars. The universe will keep turning while you sleep. Ton 618 will keep feeding, the light will keep arriving, and tomorrow night, when you look up again, it will all still be there. Waiting. Mysterious. Beautiful. Inviting you to keep asking questions. Inviting you to keep wondering. Inviting you to keep looking up. Thank you for drifting through the cosmos with me tonight. I hope you found rest among the stars and wonder in the mysteries of the universe. If you ever wish to journey to another distant corner of space, I will be here, waiting. Sleep well.